This lab is going to talk about rivers, floods, flood hazards, and predictions. And we're going to start off first just looking at some of the natural shapes of rivers and the natural conditions in rivers. And then we're going to use some data to actually predict the flood frequency in an area in New Jersey that commonly floods, known as the Greenbrook River. Water, again, is probably the most important physical agent on the planet to shape the surface of the earth, and it carries tons of water, tons of sediment, and redeposits this sediment in different places. And floods cause more damage and kill more people than the earthquakes and volcanoes combined. So this lab will first discuss some of the basic stream processes and the shapes of streams, and then take some real stream data and actually calculate some of the flood frequencies in the Greenbrook River area. First, the hydrologic cycle. I'm going to draw a cross-section of a stream. Here's the stream valley, here's the stream channel, and the stream valley. And when we have precipitation falling, PPT, on the Earth's surface, the precipitation can do two things. It can actually just directly run off and go into the stream valley, and this is called overland flow. Or it can infiltrate into the ground surface and travel through the ground as groundwater and enter the stream underground or towards the edge of the stream. And this is called base flow. Okay? When there is no precipitation and you just have the water in the stream, essentially all the water in that stream is coming from groundwater or base flow. When you do have precipitation, what is going to happen is the stream level may get higher, and if it gets too high, you may actually go over the banks, and this is called the bank height. You may go over the banks and actually flood the floodplain. So these two combinations of overland flow and base flow together are also called runoff. I'm going to talk about now drainage basins and drainage divides. And a drainage basin is the area that's drained by a stream, a given stream, and it can be very large or it can be very small. It can contain one stream or it can contain several streams. In this diagram, you can show how you can separate one drainage basin from the adjacent drainage basin. If we could continue this over a little bit, the two drainage basins are separated essentially by a topographic high point called a drainage divide. As far as the United States goes, the biggest drainage basin is probably the Mississippi River drainage basin, which covers nearly 2/3 of the continent. Now, streams also carry sediments. They're the biggest erosional process, and these sediments are transported and then they're deposited, and the deposits are generally called just alluvium. And we'll come back to where some of these deposits occur in streams in a minute. But first we're going to look a little bit at the stream shapes. Now the stream shapes are going to depend on several factors. First of all, they're going to depend on the geology that the stream is running across. If the land surface is relatively flat, you're going to have one kind of a stream shape. And if the surface has a lot of ridges and valleys, you might have another kind of stream shape or pattern. The next thing is actually gradient, or the slope that the stream falls. The gradient is essentially equal to the slope of the hillside. And to figure that out, you could just draw kind of imagine a triangular diagram where on this axis is basically differences in elevation. The second thing you need for a slope is you need to know how far that's going, so we have a horizontal distance. Now usually these are measured in feet or meters, and the horizontal distance is usually in miles or kilometers. And essentially, we can draw this diagram. Now what you'll do to figure out this elevation difference is you'll look at topographic lines on a map. And you'll see that where the stream starts and where it ends, where you want to measure it, and take the difference of those two elevations. And then also on the topographic map, you can figure out the distance. You can either lay a ruler on the map and compare it to the scale, or a piece of string if the stream is really wavy, and you'll get a distance in miles or kilometers. And so the gradient is calculated by putting the elevation difference as a numerator, dividing it by the horizontal distance. And usually we keep the units in either feet per mile, or in meters per kilometer. The next thing that controls stream shape is the base level. How low can the stream erode before it hits like a body of water? For example, a stream draining into the ocean, the base level is going to be the ocean. It can never go below the ocean's elevation. But it could be much higher if it's draining into a lake or another river. So the base level is basically the lowest point that stream can cut down before it ends up in another body of water. The amount of stream flow that's measured is called discharge. And discharge is essentially the volume of water that flows past a given point per time. So it's the volume of water that flows past a given point per time. And this is usually measured in something like cubic feet or cubic meters or cubic miles or gallons per time. And the load is actually the sediment that's carried in the stream. And that can be anything from large pieces of gravel to fine clay and silt. So the shape of the stream will depend a little bit now on the gradient and on the amount of sediment that it's carried. Refer to your lab book and you'll see a picture in the upper right that shows a picture of a stream shape that's called braided, meandering, and straight. Now, streams don't usually have a straight pattern for very long. If they have a lot of sediment load and a very steep gradient, they tend to have the braided shape. But once they get down to a lower, shallower gradient, and maybe some of the sediment load has already been deposited, they tend to become more meandering. And the places where these sediments or the load is deposited can vary between these two streams. In the case of the braided stream, the sediment is usually carried on these channel bars in the middle of the river. However, on a meandering stream, you tend to have erosion on the outer bend of the stream, where the stream curves outward. You tend to get deposition on the inner part of the stream on a point bar, and that's the part that kind of sticks out into the stream. That essentially is what causes the floodplain to be generally flat over a broad space. Now, the way geology controls the stream channels or drainage patterns is as follows. A dendritic pattern will develop usually on something that's kind of flat lying. And a dendritic pattern is kind of like the branchings of the tree, or you can think of your hand, all your fingers being the branches of a stream all meeting up to a major stream. And that usually occurs on a relatively flat surface where everything is kind of equal as far as geology is concerned. Now, a rectangular pattern will develop usually with right angle bends, usually on areas that have ridges and valleys. The main branch of the stream runs down the center of the valleys, and the kind of perpendicular streams kind of run down the slopes. And similar to that is like a trellis pattern, which just has a lot more of those kinds of connections. A radial pattern commonly develops around a topographic high, such as a volcano or a hillside. Another one that commonly develops is called distributary. It looks like the opening of a fan. So those are the main ones that we're going to deal with in lab today. So we have the basic kind of shapes and the geology and the kind of taken care of. But now we're going to say, how do we actually predict what's going to happen in a flood? And to do this, we're going to actually take real data from the Greenbrook River area, which runs through Plainfield and Greenbrook and ends up in the Raritan River. And this river or stream commonly floods in major hurricane events or major rainfall events. There's been a major flood in 1955. In 1973, a smaller one in 1996, and then many of you may remember Hurricane Floyd in 1999. Well, during Hurricane Floyd, there was up to 10 feet of water flooding the downtown of the village of Greenbrook. And so it's very important, especially in urban areas, to be able to predict the severity and frequency of floods. So let's take care of just a few definitions of some flood characteristics, and I'm going to draw a cross-section on the board of our river. Here's our river channel, and typically the river is flowing slightly below its upper bank. Now, on this part, with the water is completely filling the channel, we say that the stream is at bank height. So that is the maximum that the stream can carry. And that's kind of the average maximum flow. Any stream that you look at, its bank level will be kind of the maximum on average that the stream will carry during its maximum flow. Now what happens if it goes over again, if we have more than will fill the bank height, we end up having what's called a flood. And we've heard the word flood stage. Well, stage is another word for essentially height. So you could call that flood height or flood stage. And when you have a flood, you get to the maximum of the flood stage, and that's typically called the crest. The flood is going to crest at so many feet above normal. Or the flood can be expressed as either its height above the bank or the stage, or it can be expressed as the volume of water or the discharge that's coming down the river per time. And we're going to see how we can relate those two together in a minute. Now, the other thing that's done with a lot of stream data is what's called a stream hydrograph. And this essentially takes, over time, the amount of discharge of a stream versus time. And there's an example in your lab handout basically for a whole year. And this is kind of a typical one for an area like where we live, where tends to be some snow cover and snow melt in the periods between March and April, perhaps. And then usually the summer months have a lot more rain on average, so the discharge is higher. And then again, in the winter and fall, we have less rainfall. And the lowest point on the hydrograph is typically called the base flow. And remember, before, base flow is essentially just groundwater flow into the stream. You can also draw a hydrograph or make a hydrograph for a single storm event. And this is shown in this figure, where we have it, the hatchered area shows the period of time that you had rainfall actually happening. And the solid line represents the height or discharge of the stream with time. And you can see that the stream would, at a certain time after the rain begins, you have a maximum in the discharge, and then when the precipitation stops, you have the slow decline of the discharge with time. And you'll notice that there's a period of time between sort of the average of the rainfall event versus the maximum height of the hydrograph curve, and that's typically called a lag time. Why do you think the reason is that we don't have immediate response in the stream? Well, remember that rain has to infiltrate, and it's going to do some traveling underground perhaps before it gets to the stream. So there's always a little bit of a lag time between the time of the rainfall and the maximum peak in the stream. Now, what happens if we start urbanizing the area or building on it? Well, first of all, what's going to happen to the ground surface? We're going to have the same rainfall event, but what's going to happen now is that the water can no longer infiltrate into the ground. So we not only get a much faster response of the maximum in the stream, but also look, it's much higher than what it was under, say, natural conditions. And that's because it doesn't have a chance to go into the ground and be absorbed and then slowly leak out towards the stream. So the effect of urbanization is twofold. It not only makes the stream much more flood prone, but it also makes the stage or the height of the flood much higher than it was under natural conditions. So how do we actually take this data that for an individual storm or for a given year, or do some predictions to calculate the flood recurrence times? Well, we do that by taking several different kinds of data from the streams themselves. And one of these is going to be, we're going to measure the actual discharge and relate that to the height of the stream. So here's a cross-section of a river divided up into several little boxes, kind of vertical boxes. And on the side is a well drilled into the bank, which is connected to the river, so we can actually see how high the water is within this well. So in order, to measure the discharge, what one has to do is essentially figure out how deep the river is and figure out what the velocity is coming down the river, and you do this over the whole width of the river, and then you have to do it for different stages of flow, whether it's the lowest base flow or the highest flood stage. And you can imagine that this is kind of a pain if you have to go out there in the middle of a storm and try to measure this. So what's typically done is that you make a graph where you combine this discharge value with the height that the water is in your little well. And you essentially make a curve that relates the gauge height, which is how high the water is in this well, with the discharge. It can be a straight line, it can be kind of curved, depends on the stream. And once you've done that for the stream, it's good to go for a while unless there's a major change in some of the development. Now the other thing you do is you try to predict the flood frequency. And The way you do this is to take, you have to have a stream that you have many years of record, say at least 50 or 60 years where you have kind of these hydrographs developed. And you take, for any one of those years, you have the maximum flow for that particular year. And you basically list all these maximum flows for that given year, what was the biggest flow for that year, and you rank them from the highest or the biggest flow to the lowest. And let's say, for the sake of argument, because that's what we're going to do in lab, that you had 60 different years of record. Essentially, what you're going to calculate is the recurrence interval, or in other words, how often would a flow of a given size occur in a given year. The way we calculate that is the recurrence interval is equal to our number of years of record plus 1 divided by the rank. So N is the number of years of record, and M is the rank. We want to rank these. We call the highest one number 1, and the lowest one, in this case, number 60. So let's say we want to calculate the recurrence interval for the maximum flood. Well, basically, we know that the maximum flood is only going to happen, since we only have 60 years of records, it can only, on average, happen every 60 years. But to calculate that, is essentially 60 plus 1 divided by the rank, which is 1, so which is about 60. And this is in years. Okay, now say for the minimum one, what would that be? N would be, again, 60 plus 1. There's 61 years, or 61, but what is its rank? Its rank is 60. So for the minimum flow, it's essentially, R is essentially 61 over 60, which just about equals 1. So that could happen almost every year on average. We can also turn that into a probability. The probability is essentially 1 over R times 100. And we're going to use those two numbers to kind of guesstimate the frequency of floods in the Greenbrook River area. Okay, so now we're ready to actually start the lab. And the first exercise will simply be a map out of your lab book that shows some high elevation on the right-hand side, an alluvial fan that's draining the highlands, and essentially a stream that's down in the valley. And you just have several questions that you're going to answer, such as where do the sediments come from that are accumulating in this alluvial fan? We're going to also do a couple of calculations of stream gradient. And how are you going to do that? We want you to do one in the area of the highlands, and essentially just pick two contour intervals, high one and a low one. I think there'll be some string available in the lab, so you can lay the string along the stream itself, or you can use a ruler and kind of guesstimate. And you're going to compare that with your scale. So you're going to get an elevation difference from the topographic contours, and you're going to get a map distance using your string or ruler. And you're going to do that for several places. One is going to be up in the highlands, in this green area. One is going to be on this alluvial fan, and one is going to be down in this, on the Madison River at the bottom of the valley. So you're going to compare the stream gradients for those three things. And then the next thing you're also going to do is try to tell us what is the drainage pattern by comparing the pattern that you see of the streams in the map with the diagrams that we showed earlier in the lab. And they're not going to look perfect, but you're going to try to do the best guess of what they look like. And then a question about how do you think that the stream gradient affects basically the drainage pattern. The next exercise is really going to talk a little bit about the New Jersey drainage patterns, just to bring it a little closer to home. And to do that, again, we're going to relate kind of the surface topography with the drainage patterns. And on the left here is a picture of our map of New Jersey showing a sketch of the topographic highs and lows. And there are several provinces. One is the Appalachian Valley province, which is made up of a series of parallel ridges and valleys. Next is called the Highland province, and that's somewhat similar to the Appalachian Valley province, but the ridges and valleys aren't quite so regular. Then we have what's called the Piedmont province, which is actually where Newark fits in, and that's where we have some mixtures of fairly flat-lying sediments and then some outcrops of basalt that you'll remember seeing in Roseland Quarry. And then we have the coastal plain, which is generally fairly flat or very shallow gradient. Now this figure on the right-hand side of the handout shows the typical drainage patterns. Now essentially, New Jersey has, running almost down its middle, a topographic divide or a drainage basin divide. Half of the water in New Jersey flows eastward towards the Atlantic Ocean, the Hudson River, and New York City, and half of it flows westward or towards Pennsylvania and ends up in the Delaware River and Delaware Bay. So what we want you to do first is look at this map and see if you can draw a line kind of through the middle of New Jersey that separates the two drainage basins. And the other way you can tell this is that you'll see streams kind of ending, and you'll see streams ending on one side of the map and streams ending on the other side of the map. And what do you think might happen in between? Perhaps that's a drainage divide. So you'll try to find those places on the map and kind of draw a line through it. The next thing you're going to try to do, and I know this isn't perfect, but just look at the coastal plain in the south of New Jersey and compare it to the very northwest corner of New Jersey, which is the Appalachian Valley province, and see if you can kind of match up the kind of drainage patterns with the patterns that we gave you. And the third part of the lab is essentially going to be exercise in taking the data that I described about how to predict floods and apply it to the Green Brook River area in New Jersey. And again, there's some extra information about the severity of the flood in that area. And essentially this is of concern to people that live in the area because it really costs a lot of taxpayer dollars to pay for things to help prevent the floods, like building roads higher, building barriers and levees around the stream. All told, it's probably going to be about $30 to $50 million. So let me just show you on this topographic map what the areas that we're going to be looking at today. Outlined in blue here is the actual shape of the Green Brook River. And then just below the North Plainfield is where the gauging station was. This is where the actual data was taken. Again, the higher elevations are actually the Watchung Mountains, and all these rivers flow into essentially into the Raritan River drainage basin. So what we're going to do is take some of this real data from the Green Brook River area. And the first thing we're going to look at is some yearly discharges from the Green Brook River area plotted over several years. And there's two graphs that we're going to use. We have one from 1950 to 1956, and essentially this is several years where we have the discharge again on the left in cubic feet per second, and essentially time on the x-axis. And these look a lot noisier than the simple graph that I showed you. Each one of these peaks is a single storm event. So we'll have many of these peaks throughout the year, but on average you can see there's kind of a humped curve similar to the hydrograph pattern I showed you before. We have another set of patterns from 1970 to 1976. Now we have several questions that we are going to just relate to these figures. Might be a question about asking when was the maximum hurricane in 1955. So you'll look at the year of 1955, see if you can find the maximum peak. To figure out what the actual discharge is, you go from the maximum peak, follow the line over to the left-hand side, and actually read off the discharge. What is the minimum discharge in any one of these maps? What does that or graphs? What does that refer to? And again, remember that the minimum discharge is typically the base flow, or that stream. And you can see in different years it may be at different amounts of discharge, but essentially the lowest discharge is the base flow for that year. Then we're going to ask you some questions about some differences between these two periods of time. Now, in the 1950s, you can well imagine that this area was not as well developed as it is even in 1973. We want you to, first of all, just look at the characteristics in the pattern, and then see if you think there's a difference between the two, and answer a question about why you think that difference has occurred. Now we're going to actually take the data from the stream discharges and do a rating curve and a flood frequency curve. So on page 15 actually is a listing of the 60 years worth of data of the maximum discharge for the Green Brook River. And they're ranked again from the maximum discharge to the minimum discharge, given the gauge height, and that's in feet, and the ranking of, which is M, from 1 to 60. We want you to just calculate a few of the recurrence intervals. We filled in most of them for you already, but we just want you to practice calculating a couple of them. You'll calculate the recurrence interval and the probability and fill in the blanks. Now, to make your rating curve, we have to relate this actual discharge that was measured versus the gauge height. And that'll be done on the graph. We label part D, number 4, and this is our rating curve. So what you'll do is you'll take the discharge, which is the first column of data after the date, and the gauge height, the second column, and so for each one of these, you'll match the discharge with the gauge height. And you don't have to plot every single point, but you should plot all the ones at the highest rank because there aren't too many of them. But as you get to the lower ranks, you can just maybe plot every second or third or fourth one, just enough so that you can get an idea of the shape that the curve is going to have. And the purpose of doing this is just to get you used to being able to take, 2 sets of data and actually plot it and understand what a graph will give you. So now we've got our rating curve. We need the next bit of information, which is a recurrence interval curve. And we've already plotted the data for you. This is on special graph paper called probability paper. And again, it plots the discharge on the one axis versus the time or recurrence interval, and that's actually in number of years. Now, to do something useful with this data, we have to kind of draw a straight line through those squiggly points. So just draw your best guess of a straight line through those points and kind of extend it beyond at the lower end and at the upper end, and go with a straight line. We're going to ask some questions now about what you marked on your hydrographs for 1955 and 1973 and start to relate them to these flood frequency curves and rating curves. So one of the questions is, like, you pick the highest discharge for 1955, the hurricane event, and you're going to tell us how often in number of years could a flood of that magnitude happen. So in order to do that, you take the discharge of that particular flood and you go horizontally till you hit your line, and then you go downward to read off the number of recurrence interval in number of years. And you're going to do that not only for the 1955 flood, but there was also a hurricane event in 1973, and you'll do the same kind of thing. And then you're supposed to say, wow, these kinds of floods could happen fairly often. And you'll find out that they're commonly less than 5 years. Well, we're going to take this graph and say, well, what would the discharge be for a 100-year flood? And that basically is remember our data only went for 60 years, but you can extrapolate to higher numbers of years by just extending your straight line. And although this is, kind of fuzzy out there, it is an estimate. So what we want you to do is estimate what the discharge should be for a 100-year flood. And we're going to see what part of the Greenbrook River area will ultimately flood by comparing that discharge with our rating curve, and then actually relate it to what elevations would actually get flooded. So to do that, we have measured off our maximum discharge for a 100-year flood, and it's going to be somewhere above like 2,000. We go back to our rating curve and figure out, okay, if our maximum discharge was somewhere above 2,000, it's going to be somewhere up in here. And we're going to actually read off, well, how many feet above the base level of that, where that measurement was taken, will that flood occur? And we see that it's 6 feet above the base level, which was at 70 feet of elevation. So you add the two together and you can round it up to the nearest tens just for the sake of argument. And that's how high the Greenbrook River will flood at a 100-year flood. So now, to put this in terms of actually what's going to happen in this river, we've got 2 additional exercises. And one is just simply, we've taken a cross-section, and it looks kind of exaggerated, but we have a cross-section essentially across the river from the Watchung Mountains over to the valley. And now that you know how high the river is going to flood, essentially everything under the cross-section would be solid ground. These dips obviously are these stream valleys. There's actually a couple other little tributaries. So now you're going to fill in like what area of this cross-section in terms of just elevation is actually going to get flooded. And you can just fill that in with some colored pencils. And the other thing, we've duplicated a portion of this map, and again, you're going to now color in all the elevations that are going to be flooded during the 100-year flood. And you might need to refer to the actual topographic sheets because it's a little hard to read the contour lines, but once you've kind of got it, I think it won't be too hard to trace out the contour lines that are going to, the maximum that is kind of like the upper limit on each side of the river. And you'll find out that a good portion of this map is going to be covered up with water. And then we have a few questions about like what kinds of things do you see are getting flooded. You'll notice that there's schools, there's sewage treatment plants, there's the the Northeast Corridor tracks. All these things are right in the middle of this flood-prone area. Okay, so then the last question is just a thought question of what might be a better use of the area adjacent to the stream instead of having it completely developed with houses and factories and so on.